Okay, in this lesson, we're going to work on making conversions where we are dealing with a metric measure of area or volume. I'm going to go back to the little, the lineup of abbreviations here that we need to keep in mind. K stands for kilo, H for hecta, DK for deca, and then our center measure is our unit, our gram, our liter, or our meter, one of those three. It's liter if we're dealing with volume, gram if we're dealing with weight, and meter if we are dealing with length. Then we have deci and centa, and then milli. Again, this is 1,000, 100, 10, our single unit, a tenth of a unit, a hundredth of a unit, and then a thousandth of a unit. One way that you can kind of remember this is a little phrase called King Henry died unexpectedly drinking chocolate milk. So that might be a little lineup to help you. Again, King Henry died unexpectedly drinking chocolate milk. Okay, so we're going to refer to that again. What I want you to remember is that you're dealing with area, which means you're dealing with square area. Volume, you're dealing with cubic volume. In other words, area is two-dimensional, volume is three-dimensional. Let's see how that plays out. Okay, to convert between metric measures for area and cube, you need to account for that squaring or cubing of the measure. What I want to do is kind of draw a picture here so you can see what's happening. In this case, I've shrunk a picture here, but this is meant to be 1 meter, which is, we all know that that's equal to 100 centimeters, by 1 meter, again, equal to 100 centimeters. If I was trying to find the area of a square meter, 1 meter times 1 meter, in other words, length times width, would give us 1 meter squared. But if I converted that and put that in terms of centimeter, I would be saying 100 centimeters times 100 centimeters. When I carry that out, 100 centimeters times 100 centimeters, I end up with 10,000 centimeters. So you can see that, changing our place value here really magnifies when we go to find area. So in short, you can think about this. Back when we were dealing with our King Henry statement here, we knew that we were going from meters to centimeters. That was a movement of two place values. So that's what happened here when we're looking at just one-dimensional length. But when we go to two-dimensional area, you can see that our movement changed double. We went from 1 meter squared to 10,000 meters squared. So I've kind of written that here. 1 meter squared is equal to 100 centimeters squared, which would be 10,000 centimeters squared. So you can think about this going from meters to centimeters, squared meters to squared centimeters. Our movement doubles. So in this case, we're going to go from 32 meters squared to centimeters squared. We know that there's an implied decimal. So initially we're thinking, okay, there's an implied decimal here. I have to go 1, 2, but it's double the movement. So I'm going to go 2 more. So it's actually, I'm going to be tacking on 4 zeros here. So 32 meters squared is equal to 320,000 centimeters squared. Going the other direction, if we're going from centimeters squared to meters squared, again, I'm going to write my number down here. And I know that going from centimeters to meters, we're here at centimeters. We go 1, 2, place values back, so that's 1, 2, but we're going to double that because we're looking at square area. So this would be 14 hundredths. So when you're dealing with area, just remember, movement doubles. Okay. Now we're going to go and we're going to take a look at volume. Here we've got 3.6 meters cubed, and we're going to go to centimeters cubed. So going back to this picture here, I can't really even draw this three-dimensionally, but you can think about this. You're going 1 meter by 1 meter, and we're actually going to go a third dimension here. So this is really this expansion is going to happen one more time. So in other words, I'm going to write my little number down here. I go from meters. When I'm looking at linearly, I'm going from meters to centimeters, that's a movement of 2. Sorry. I'm going from meters to centimeters, that's a movement of 2. But because this is volume, that movement is going to triple. So I'm going to go 1, 2, 3, 4, 5, 6. And then I have to place in 0. So I have 1, 2, 3, 4, 5 zeros I'm going to add in there. So I'm actually looking at going from 3.6 meters cubed, cubic meters, to centimeters cubed. We've got 3,600,000 centimeters cubed. Going from centimeters cubed back to meters, again, you're going from centimeters 2 places to the left when you're looking at it linearly, but when you're looking at three-dimensional volume, we're going to have, I'm going to write my number down here so you can see what I'm thinking here. I'm going to go moving my decimal place 2 places, and then 2 more, and then 2 more. So it's actually 6 places. Actually, I wrote that. Okay. So 56,000 meters. So when we're looking at volume, movement triples. Okay, and this is just a little statement here to kind of keep you thinking about all different kinds of conversions here. But large volumes are often measured in cubic meters, as in meters cubed. So we need to replace or relate liquid volume, liters volume, to meters cubed. This is very similar to gallons to cubic feet. We did a conversion when we were dealing with standard measures. We converted cubic feet to gallons and vice versa. We need to be able to do the same kind of thing when we're dealing with metric measures. In metric measures, 1 liter is equal to 1,000 centimeters cubed. So to give you an example of that, we might do this problem here because I want you to see how this would be used. We need to convert 3 liters to centimeters cubed. So I'm going to write 3 liters times, and now I need to convert and use this equivalency, or I could use this one, it wouldn't matter, but I'm going to go with this one. And I need to put the 1 liter in the denominator so that my liter measure eliminates, and then I've got 1,000 centimeters cubed here. That is going to be equal to 3,000 centimeters cubed. And you're like, when would this ever be useful? Anyone who would be working in a hospital and maintaining doses of, any kind of antibiotic, medication, or even saline solution, you very often purchase those things in large containers. A 3-liter container is not uncommon. And let's say you need to decide how many doses you have there. And doses very often are communicated as cc's. I think that comes from centimeters cubed, basically. This term right here is very often converted and called cc's. So I've created another problem here. We want to assume that we've purchased this 3-liter container of saline, whatever, and we need to identify the number of 100 cc doses. So what we would do is we would make this conversion, the 3 liters, converting it to 3,000 centimeters, and then we're going to take 3,000 centimeters and divide it by the number of doses we have, and know that in that container we have 30 doses, each being 100 centimeter, or cc's. Okay, the last thing that we need to do in this video is we need to make some conversions between temperature. I think some of us are getting better at converting between Celsius degrees and Fahrenheit degrees. We have these 2 formulas that we're going to use. Some of these things I know many of us know that in Celsius, freezing is 0 and boiling is 100 degrees, whereas in Fahrenheit, freezing is 32 degrees and boiling would be 212 degrees. A lot of times I'm kind of amazed a lot of students don't recall that. As far as body temperature is 98.6 in Fahrenheit. Those are probably measures that we already know in terms of filling in that information. This one here, we're going to use one of our formulas here to convert 98.6 Fahrenheit back to Celsius. And so we've got these two formulas, and we have to decide which one we're going to use. Okay, so if we are given Fahrenheit, we're going to use this formula, where Celsius is equal to 5/9, and then in parentheses, Fahrenheit minus 32. So we're going to plug in 98.6 for this F here. So Celsius is equal to 5/9, and we're going to plug in the 98.6 and subtract the 32. Now, at this point, this is just really an order of operations problem. We have to make sure that we do what's inside the parentheses first. So we're going to go ahead and carry that out, and we'd end up with, it could end up with, actually that goes in there 5 times perfectly. Sorry, doing the wrong thing here. So when I subtract that, I end up with 66.6. I could go to the calculator and then identify 5 divided by 9, and I'm going to get some decimal notation. But I think it's probably easier just to say 5 times this 66.6 and then divide by 9. And you should come up with right at 37 degrees. Okay, so we could fill that in there. Over here we're going to go from 18 degrees Celsius, and we're going to convert it to Fahrenheit. So we're going to be using this formula here because we've been given Celsius. We're going to plug that in here. So Fahrenheit is equal to 9/5. We're going to plug in our Celsius degrees of 18 and plus 32. So I'm just taking this 18, plugging it into this formula right here and bringing everything else down. Okay, with your calculator, I think it's probably easier just to say 9 times 18 divided by 5. You can do it however you want. But you should end up, by the time you add the 32, you should end up with 64.4 degrees Fahrenheit. But again, both of these are order of operations tasks. And I just want you to note that over here, we subtracted 32 and then multiplied by 5/9. Whereas over here, we multiplied by the inverse of this coefficient, 9/5 is what we multiplied by, and then we added. So you can see that these are similar, and you got to make sure that you grab the right formula.